Good afternoon, everyone. My name is Benjamin Debucher, and I'm the Head of Events Program at JEC Group. Thank you for joining us today. Today's webinar is MolecularGRIP, a major leap forward in solvent-free surface functionalization for adhesive bonding. As you all know, bonding different types of materials can be challenging. During this webinar, Molecular Plasma Group will introduce its MolecularGRIP range of solutions, which are based on its proprietary molecular plasma technology. MolecularGRIP addresses many of the challenges of the composite industry, such as adhesive bonding of dissimilar and inert material, and also sensitive materials, as well as EHS concerns related to solvent-based primers. Additionally, surface functionalization with MolecularGRIP is permanent, which enables storage of pre-treated parts for many weeks. We will discover in this webinar all the advantages of MolecularGRIP, its competitive total cost of ownership, how it is easily scalable and a solvent-free process that operates at room temperature, how it works on any material, the inspection and traceability of the treatment, and as I mentioned earlier, that there is no EHS concern. But let me introduce first Molecular Plasma Group. MPG is a spin-off from two research institutes, Vito in Belgium and LIST in Luxembourg. Created in 2016 and based in Luxembourg, MPG has subsidiaries in Belgium and in the UK. MPG offers a disruptive key enabling technology that enables the creation of a wide range of advanced surface functionalities. As a full service provider, MPG offers application development as well as design, construction, and servicing of equipment ranging from lab system for R&D center and universities up to industrial inline system for continuous production. We will be hearing from Mark Jacobs, CEO of Molecular Plasma Group. Mark holds a master's in engineering from the University of Leuven and a master's in leadership and strategy from London Business School. He is a serial entrepreneur and author of the book Negotiate Like a Local, 7 Mindsets to Increase Your Success Rate in International Business. We will be also talking to Bernard Nissol, lead scientist at MPG. Bernard holds a master's degree in chemical sciences and a PhD in materials and plasma chemistry, both from the University of Brussels. Prior to joining MPG, he worked as research associate at the Polytechnique in Montreal, designing plasma reactors and developing plasma coatings. So, are you looking for ways to revolutionize plasma-based surface functionalization? Do you want to know more on how to bond different materials easily? MPG has the solution, and this will be presented to you in the next 60 minutes. Quick reminder for our audience before we start. We will be taking questions at the end of the webinar as usual, and you can start asking your question in the question tab here on the right of your screen. I will be reminding you again during the webinar. You have also the possibility to upvote the questions from other participants. As usual, I recommend you to be connected through cable wire rather than Wi-Fi if you want to maximize the experience of the webinar. But in any case, the webinar is being recorded, so you will be able to view the entire program later on gccomposites.tv. So let me now open the floor to Mark Jacobs, CEO of Molecular Plasma Group. Mark, welcome online.
Thank you very much, Benjamin. Thank you very much for the very kind introduction. And I would like to reiterate the word revolutionary, because I'm quite sure that mostly everyone in the audience knows about plasma, knows about Corona, and thinks, okay, I know it. Yeah, what's new here? Well, it's really very, very different from anything that I would think most participants know. So I would like to start just by showing you a little video that gives you an idea of the type of stuff that we can do. So on the left, so basically you see an ETFE film and an acrylic foam test tape. On the left, untreated material, and obviously it doesn't stick. On the right hand side, once we've treated it with the methacrylate function, there you go. The tape just sticks on the ETFE, and I'm sure that you know that that is not a simple feat. Those are the types of things that we do. Let me give you, to get started, a few references, companies we work with. There's a lot more. You can see all the dots appearing on the map. There's many more companies that we work with. Most of the stuff we do is under confidentiality agreement, so I can't mention a lot of the names I would actually love to mention in this webinar, but that's life. But it gives you already a good scope with industrial companies. You see universities, RTOs across the board. So when we talk about major industry challenges that we address, what are we talking about? We're talking about inert materials like polypropylene, Teflon, ETFE, other fluorinated polymers, notoriously difficult to bond to, but also more sensitive materials like PLA or even cellulose-based materials. That's one. Second, a lot of the time the priming is organic solvent-based, which creates all kinds of environmental health and safety concerns. The third one is that in many production processes, it would be great to have a large open time. And a lot of the current processes, be it Corona, be it organic solvent-based, have a pretty limited open time, also have waiting times, flash-off times, etc. All that we address. And then on top of that, we can actually also offer a complete inline process control over the priming operation. So you heard already a little bit about MPG. Who are we? We're based in Luxembourg, where we have a plasma lab and manufacturing. We have a lab in the bioincubator in Belgium, where we also have a training center, and we have a sales office in the UK. We start from application development all the way up to the design and building and servicing of industrial solutions. So we're not just a research lab. We really tackle problems and scale them up to robust industrialization. And with that, our technology is very well protected. We have 19 patents today. So with that, we have a solid, safe base. But what is molecular plasma? What are we talking about here? In the end, it's a technology that, as we already mentioned, enables surface functionalization of highly inert materials like Teflon and polyprop and highly sensitive substrates. And we use atmospheric plasma as a vector to graft a range of organic chemistries onto any surface. So contrary to Corona or other open air plasma types systems, that actually where the plasma itself creates the function. For us, the plasma is, I shouldn't say only, but still is the vector to really bring an organic chemistry onto a surface and bind that covalently onto that surface. And because we bring a different chemistry specifically to the surface and graft it, that results in a permanent surface modification. So you don't have any decay or anything like that. So then you can start to think about, the range of chemistries you can use and the type of applications you could use that for. And today's focus is on our MolecularGRIP technology, where it's really about priming surfaces for adhesive bonding. But we also work solutions for hydrophobicity, hydrophilicity, phytocidal functionalities, and even biomolecule deposition. And I want to just dive into that last one a little bit more, just to give you an idea of the difference of what we can do. Imagine that you can introduce antibodies or peptides inside a highly reactive medium, which a plasma is, inside that plasma, and not destroy them, not blow them apart, but fix them onto a surface and keep that full biofunctionality. That is what we can do. That is what that tells you how much control we have over this process. A little video to kind of capture that in a few images. So we can do it on for difficult to bond and sensitive materials, but essentially the technology is, I call it substrate agnostic. Whatever your material is, metals, plastics, natural materials, you name it, we can do it. We have not come across a material yet that we cannot treat. So then here's a schematic representation of what we do. We take a gas and we turn that into a plasma. We use an inert gas. We don't use air, as you can imagine, because if you give oxygen, energy, and chemistry, that would not give enough control. So the plasma actually activates the surface, and at the same time, we bring in the precursor chemistry. And just as Bernard likes to call it, tickle the chemistry. So just open the weakest bonds, call it activate that chemistry. And we bring that to the activated radicalized surface, and the two recombine and have a permanent modification, permanent chemical modification of that surface. So that way you can bond any material onto anything else. Key things, it's single step, ambient, covalence bond, is durable. You can use a wide range of molecules and really on any surface. I'll come back to that discovery day concept later in the presentation. So if you look at it, look at this video. On the right-hand side, that's us, and we're treating a piece of paper. And the left is a traditional torch, which obviously when you light that up, you can see it burns the paper within a second. Whereas with our torch, nothing happens to the paper. We can actually treat paper stationary for an hour and you will see no degradation. That's how different our technology is. Put that a little bit more in some more technical perspective. So we are at very low temperature. We actually at room temperature. So we don't heat the substrate at all. So therefore we can use very sensitive substrate. We're at very, very low energy levels. The plasma does activate the surface. We can easily activate the surface, no problem. But with the corona, you're also going to etch the surface. And then when you introduce organic chemistry, in our system, it remains intact. In any other higher energy system, you will blow it apart. So in our system, we have no arc, so we have a homogeneous glow, which means that you will not destroy the chemistry. There's no electrode erosion, room temperature. We can use any carrier gas, as long as it's not explosive. And all that together enables us to introduce organic chemistry and even biomolecules. And we can do that from a tiny spot size up to, here we say 1.2 meters, we can do more, continuous curtain, whatever your needs are.
Mark, sorry to interrupt. I have a quick question for you. Why do you emphasize the use of organic chemistries? Well,
if you when you look at the development that Vito did, the market is mostly going to high energy systems, and Vito deliberately went the other way to see how low we could go in the energy, and that exactly with the aim to introduce organic chemistry. So the niche that we have compared to everything else out in the market is that we are, I would say, probably the only ones in the market, as far as I can tell today, that can do what we do with a wide range of chemistry, sensitive organic chemistry. Mostly every other system out there is too high in energy and will destroy that chemistry. So therefore, we have a unique niche that enables very unique solutions, and we focus specifically on that. We have no intention of going higher up the energy range and go and compete with systems that already exist.
Thank you, Mark. And I remind the audience that you can ask your questions to Mark and Bernard by typing them in the question tab on the right of the screen. Thank you.
Now we're just going to show 3 case studies to give you a flavor of the things that can be done. So here we talk about adhesion on polypropylene, where the issue is adhesive failure between the glue and the polypropylene and a very short open time. So the current solution that's in place, it's Corona pre-treatment, and net the shear strength is too low and the open time is too limited. So you can see in the graph the level of shear strength with Corona. And here you see 3 different chemistries that we can apply and that we validated that have a better performance than the Corona, and that also have a very long open time. So we actually have 90% improvement versus the existing situation, and additionally, essentially an unlimited open time. So with Corona, the open time is typically a few hours, maybe a bit more, and we are in the weeks, months. For practical purposes, it's essentially unlimited. Case study number 2. Here it's aramid textile to elastomer, where it's also about improving adhesion, where you see here the existing solution, where we did several different developments with different precursors. So it's really important which chemistry we use, and so that's always, let's say, requires some development work. So with precursor number 1, we're roughly there, but not quite. With precursor number 2, we're definitely better, but we still have an adhesive failure. With solution number 3, we go into a cohesive failure mode, and we're way ahead of the current solution. Case study number 3, it's about metal to polymer adhesion without any glues, where the result with an untreated metal wire, you have this pull-out force. Depending on the chemistry we use, we obtained a 5-fold improvement. So those are just 3 case studies to give you a feeling of the scope, and they're by no means limiting to what we can do. It's just to give you a feeling for the type of things we do. Now I want to actually dive a little bit into the system. How do we really do this? Well, here you see a cross-section of our indirect DVD plasma, where you have a high voltage electrode, a dielectric, and the ground electrode, which is this tube here. So in between the dielectric and the ground electrode, we bring in nitrogen typically, but it can be any other inert gas, and turn that into a plasma with an electromagnetic field. And so we blow that plasma, comes out of the torch and activates the surface. At the same time, we introduce the chemistry of choice, which can be organic molecules or biomolecules. They remain protected from the plasma all the way till the end, and then just see the plasma for a few microseconds, which is enough to tickle them, but not enough to destroy them. And it's part of the whole processing to be able to do that. Now, inherently, when you see this design, you can see that it's inherently robust, because if you would introduce the chemistry in between the electrodes, you would deposit it everywhere, also on the electrodes, and you would never have a robust, stable process. With this design, the whole concept is inherently robust. Short video of what it looks like. This is a lab machine that we have in Luxembourg, and Max here is setting up for a test. So you see a little bottle there which contains the chemistry. While you're watching this, the chemistry, in our case, in order to use the chemistry, it has to be liquid. And then we generate nano droplets of the chemistry that we introduce inside that inner electrode. And here, this is the chemistry tube that goes to the inside of the head. And then the setup is like this. So the head is mounted on a 3D table. We often start just for functional development, which chemistry, which process on small bits of material, and then scan the surface. And we can do, just to give you an idea of the flexibility of the system, we can run up to 50 different process configurations in one single day. So it's really easy to change over from one to the next to the next. It's super, super flexible.
Mark, sorry to interrupt again. I had another questions from few slides before, but how stable and durable are the coatings you deposit?
The chemistry, because it's grafted, covalently bonded onto the surface, it really is a permanent modification. Then it depends on whether that chemistry actually interacts with the air. Let's say if it interacts with humidity, then it would require probably some protection from humidity. But for many applications, we can bring the functionality to the surface and have it stable for weeks, months, even years, without any special precautions. What I do want to what I do want to say is that we typically deposit very, very thin coatings in the order of 10 to 100 nanometers, and they're organic in nature. So therefore, you do need to be aware that the, let's say, the abrasion resistance is relatively limited, because nanometers organic is not going to be a hard, very abrasion resistant coating. Which also, when you actually see the case studies I mentioned earlier, it's always working on that interface towards something. We do have some applications where we deposit the top coating, but they're rare. They need to be in environments where there's no abrasion.
Okay, thank you, Mark.
We can also adapt nozzles onto the plasma heads. This is a fiber nozzle where we stick this onto the plasma head and then just can coat fibers. And this is what it looks like then. Then we can do first initial process development on fibers. Once that's developed, it can be scaled up to robust solutions. In a quick overview, so today, because in the end we manufacture machines, robust industrial solutions. Here you see the plasma head mounted on a robot that you can just integrate into your production line, basically just like that, for if this suits your application. We have freestanding systems, the Mini and the Maxi, which we use for either development work or small production, small series. Quite a few of these are actually, apart from in our labs, we also have them at a range of universities and industrial companies that do their own application development with them. A new one that we're just bringing to market is actually powder treatments with our plasma. So today, it's a combination of our technology and Procept's technology. Procept is a specialist in powder coating, spray drying, spray coating, all those types of things. Mostly in the medical world, actually. But we've combined our technologies, which allows us now to also do all the functionalities that we can bring to 2D or 3D surfaces, also bring that to powders, which can be of extreme interest in powder treatment, obviously, again, for the composite sector. We have some programs ongoing, but I can't say anything about them, unfortunately. So what does that look like? So here you see a fluidized bed reactor from Procept, onto which we've coupled our plasma head, and the plasma comes out here through this nozzle. And although it looks like a flame, it's cold now. And here I just want to show you this is PE powder, 150 micron PE powder, which we functionalized with an amino function. And here you see the untreated powder. This is just plasma activated only, and this one has the amino on it. And Bernard, you want to talk to this a little bit? What's going on here?
So what's going on here? So on the right side, you see untreated powder, polymer powder. That I think it was PE on that case. On the center, it's a plasma-only treatment, basically a corona-type treatment that was applied. And you can see that there's, of course, no functionalization with the molecules. Maybe you can see that there's a better mix done with water. You see that the powders that float at the surface of the liquid are not, they don't have the same aspect as the untreated ones. So something happened to the powders. Now on the left side, we applied an amino-based coating, so based on an amino-containing precursor. And actually the orange dye that you see, it's orange too, will specifically react with the amino groups that we grafted on the surface. So with this, we have a nice, quick and dirty proof that basically we have efficiently treated with amino functions the powders, because basically all the dye that was in the water initially is actually transferred to the powders and literally removed. We have filtered out the water solution from its dye, and everything is grafted on the powders. I also would like to mention that these have been standing for months in our lab, and they're still well functionalized and stable.
Thank you. So then, what we just showed you so far is all based on our plasma spot, the cylindrical type head. But for larger volumes, larger surfaces, we also have linear heads. And here the concept exactly the same. So I have voltage electrode, dielectric, an inner electrode, except that now it's linear. Yeah? And that enables us to create homogeneous curtains of essentially whichever length we like. Today, our standard solution is 400 millimeter, but we're not technically limited to anything, and we can also put several heads next to each other to make bigger, larger lengths. All that's perfectly possible. But this allows us to really homogeneously treat large surfaces, so it's not multiple spots next to each other and all kinds of effect between the spots, etc. No, homogeneous over the entire width. So this is what it looks like here. This is a lab machine where the head is mounted on top of a conveyor belt, but it can be, the mechanics don't really matter. But this is what the head looks like. Today, as I mentioned, 40 centimeters, and we now, in a few months, we'll have a 1.6 meter wide system here that can really start to do large volumes. All the systems have, fully data tracking, collection, diagnostics. They're fully industrial. I want to show you here a system that, this is a 40 centimeter system designed for roll-to-roll treatment of non-wovens. In this case, it's the application is actually virucidal. I mentioned earlier that we can do that. It's something we did, obviously directly related to the corona situation that we've experienced. So we developed a solution to treat 20 grams per square meter non-wovens with citric acid and create a fantastic virucidal function. And I'll show you just a video specifically around that virucidal, but I think it's just a roll-to-roll production platform. It can be used for any roll-to-roll material, textile, technical textile, you name it. Yeah, it's the same production system.
Companies have responded to the pandemic needs by investing in face mask production capacity. Face masks with traditional designs are difficult to differentiate. Molecular Plasma Group's innovative coating creates a new virucidal function by adding a microscopic layer of citric acid. It makes face masks safer by inactivating a range of viruses, including the one that causes the COVID-19. MPG's plasma-line coating machines are plug-and-play and easy to operate. The pure chemical is grafted on the surface instantly by inert gas converted into plasma. MPG supplies the consumables with full operational support. Face mask manufacturers are earning fast returns with MPG coating machines. MPG's virucidal technology is attracting a lot of attention and customers. Contact MPG to gain competitive advantage.
So here the notion of competitive advantage was just brought in, and I'd like to take this opportunity to give you an idea of the numbers. So for this application specifically, the total the TCO is in total cost per square meter is in the order of 15 cents, the maximum 20 cents per square meter. That gives you an idea. Depending on for other applications, it can go below 10 cents per square meter. So gives you a feeling for where we are for this type of application. Now, we talk about molecular plasma, and I want to open it a little bit up because there really is no restriction on the type of chemistry we can use. Liquids, mixtures, you can read it, even suspensions of nanoparticles, polymer solutions, you name it. So that creates this huge possibility of applications where adhesion improvement, obviously with amines, epoxies, acrylics, isocyanates, etc. But I mentioned the biomolecule immobilization, but also release coatings. Go to the opposite end. Rather than adhesion, we can do release coatings. We can do anti-biofouling coatings. We can do virucidal, antibacterial. It's really very, very broad. So in terms of size and shapes, I saw some questions come by also around 3D shapes. We can, on terms of material, we can treat anything. The most inert Teflon glass, gold, carbon fiber, it can be done. Down to the most sensitive materials, paper, biodegradable, etc. In terms of shape, we're talking powders, we're talking fibers, we're talking flat surfaces, we're talking 3D parts. And you go from a spot size today from 0.5 millimeters all the way up to 1.6 meters now. Now, to dive a little bit into the 3D, how can we do that? Well, first of all, obviously, because some of the heads, you can put them on the robot and you can be very flexible. But we can also add these nozzles, like you saw the fiber nozzle. They can be designed to espouse 3D shapes. And we can get to pretty complex 3D shapes. We do have limitations. We do need to be somewhat line of sight always. We can't go behind corners and things like that. But we have quite a big flexibility in terms of 3D parts. I wanted to talk a little bit about the inline process control. How do we do that? We have developed a technology to incorporate a UV tracer in the coating, so we can dose a tiny amount of a tracer molecule together with the functional chemistry, not interfere with the functionality of what we put down, and make the coating visible and the quality of the coating visible under UV light. Now, it's not as simple as it sounds, because actually there were no commercial solutions available to do this, so we developed this ourselves, and we now have a solution that allows us to detect the quality of the coating and correlate to thickness and quality of the coating. So if you need full traceability, inline control, we can do it. One other a little bit out of the box system is reversible adhesion, and some of you may have seen the testimonial from Damien Lenoble from the list on LinkedIn, where he talks about reversible composites. So the list, using our technology, has developed a proof of concept to have reversible bonding under influence of temperature. And this is a concept that, let's see, the proof of concept is there, but it's something that is really forms the basis towards further development of recyclable composites. And I think it's really exciting that our technology could even enable things like that and really drive recyclable composites going forward. How do we work? Because it's I can imagine that despite quite a few of you think, wow, great, but I'd like to get a feeling for what this is all about, because in the end the presentation is that's fine. But how do I engage with you to give it a shot, to get some feeling for what it could do for me? Well, we have a discovery day concept. It's a full package where we really, okay, what's your pain point? What are your success criteria? How are you going to measure, etc., etc.? And that will be an interactive process with our scientific team. We look at how can we solve your problem, which chemistries, etc., etc. Then we design a DOE together with you, design manufacture parts if necessary. And then ideally, we'd like you to come to us and work with us during a day where, as I mentioned, we can run up to 50 different experiments to see where do we need to be with which chemistry, with process, which layer thickness for your functionality. And if at the end of the day, after testing, we have, let's say, between 3 and 5 of the 50 that look promising, that's a success. Because then we hone into those, further develop the process, and then in a stage gate approach, go all the way up to industrialization. Because the beauty of what we do is once we have defined a process this way, it's robust, it's repeatable, it has a large operating window always. So, other aspect, which is really important, of course, the solution is extremely green. You've understood it already. We're on the super low energy side of the plasma spectrum, so it's de facto low energy. If we have a lot of energy, the whole concept doesn't work anymore. We essentially use no solvents. A lot of the time we use the pure liquid chemistry. We can use solvent-based chemistries, but even then the consumption would be absolutely infinitesimal. Because when you compare it to wet primer, where let's say 5 milliliters per square meter is reasonably typical, we're going to go down to 0.05 milliliter per square millimeter. So we have a 100x reduction in chemistry. So you take all that combined, that's a pretty nice environmental footprint. So when I go back to the beginning and based on what we said with the industry challenges, I think I can say we can do the inert and sensitive materials. We solve most of your EHS concerns. The open time is no longer an issue, and we can offer you complete inline process control. So that was the end of what I wanted to present to you. Here you have our contact information. So it would be great to hear from you, to see how we can help you. And as far as I'm concerned, we're open for questions now. I see some of them already been answered in the chat, but
thank you very much, Mark and Bernard, for this presentation. It was really interesting, and thanks also to Bernard and to Marnik for starting to answer the questions, either in the chat tab and in the question tab, so that's very much appreciated. Before we open the floor to questions, I have two questions that I wanted to ask you. When we were talking about your production platform, can you give an indication of typical line speeds?
The system you saw for the non-woven material, that will be running at about 30 meters a minute. So that, which then translates into the number that was on the screen of 5,000 square meters per shift. It's a bit chemistry dependent, it's function dependent. You can imagine if we have to, if a 10 nanometer layer does the job, it's going to run faster than a 50 nanometer layer. It depends. There are quite some factors that influence it, but let's say we're in that range. If you let's say you shoot from 10 up to 100 meters a minute, that's pretty realistic, obviously depending on the chemistry and the function, but that's what you need to be thinking about.
Thank you, Mark. And my second question was, in one of your first slides, you showed mostly activities in Europe. How can you support companies with global operations?
That's a very good question. The answer is pretty straightforward. What I haven't mentioned is that the original technology development with Vito was done in partnership with AFS Softal, a German family-owned company specialist in plasma reactors and generators. And we have continued that relationship, and through them, we have a partnership to support our customers globally. So with that, we can really engage with anyone on a global level and make sure that everything runs properly.
Thank you, Mark. So it's now time to open the floor to questions. And from the audience, I see that we already have many of them. So thanks very much for these questions. You can start. You can continue to ask your question in the question tab. So let's start with the first question. There is a lot. I need to go down. Okay. How do you, sorry, I'm going to put the question on screen. How do you ensure that the plasma can activate your surface, means destroy bonds on the surface, but in the same plasma, your precursor is not destroyed? Is the surface not strongly activated?
I'll think this is a question for our scientist.
And that's actually a very nice question, to be honest. So imagine we can work on different parameters with the plasma. The first one being, of course, the power injected in the plasma. And it is true that with some substrates that are harder to graft on, like typically ETFE or PTFE, for example, we have to raise the power level so as to have an actual bonding on the surface, covalent bonding. At the same time, there's a risk indeed to destroy more the chemistry, and that's why people like me have jobs here at MPG. There's two ways to tackle that. So either you can change the precursor flow. So if you have higher energy in your plasma, you can always raise the amount of precursor that you inject, so as to actually keep an equilibrium in the energy per molecule ratio, and that's a very determinant parameter. If you overfeed with the chemistry, you will not have an efficient, let's say, plasma reaction, plasma polymerization. Otherwise, if you have a too low precursor feed, you will destroy the chemistry. And we see that. We see that not only in the efficiency of our applications, but we also do XPS and infrared measurements and stuff like that to, really characterize what we deposit. So basically, if we have to work with trickier substrate, we increase the power, but we also modify the precursor feed. And even if by increasing the precursor feed we still have a problem, there's always solutions with other chemistries. We're not working with 5 chemistries. We're working with hundreds of chemistries, some of which are more resistant to the plasma energy, or have, let's say, weakest bonds that will open more easily with preserving the chemical functionality that we want to graft.
Thank you, Bernard. Next question. Paper has lots of fiber and is elastic, can be twisted and turned. How do you ensure uniform coating at submicron level? When you say paper, is it clay coated or thermal coated?
Bernard, for you again, I guess.
Yeah, well, that's a nice question, and to be honest, I can only partially address it, because indeed there's several types of paper, and we've been working basically with clay coated, I believe. I should ask my colleagues to make sure. And how do we ensure uniform coating at the submicron level? So basically we're depositing nanometric layers. So we will not, let's say we will not fill the material. If you have a micrometric surface, you will be able to penetrate the pores and the irregularities at the surface, but you will only coat with the very thin nanometric layer, say 10 to 100 nanometers. So this is how we ensure kind of a uniform yes, indeed, because we're in very different ranges of the roughness on one side is micrometric and the layer is nanometric.
Thank you again, Bernard. Next question is from Marcel. He has 2 questions. How long lasts the pre-treated surface? And the second question is, can I use it on one surface of a continuous laminate while rolling up the pre-treated laminate?
On the first one, let me answer that, and Bernard, I'm going to let you answer the second question. So, as I mentioned, it is a bit dependent on which chemistry you use, but we have many data points on different applications, including lamination, specifically lamination, where the pre-treatment, we've validated that it remains stable for more than a year. So that's what I can say on the first question. Bernard, can you take the second one?
Yes, I must be completely honest. I don't have the name of the person who asked it, actually, but I'm not sure to understand the question. So can I use it on one surface of a continuous laminate while rolling up the pre-treated laminate?
Okay. I think...
do you get it, Mark?
Well, I would expect it similar to what we do on the varicidal, where we treat one side of a non-woven. We unroll a roll of non-woven, we treat one side, and we roll it back up, without any problem, and then it's unrolled again for the next manufacturing operation. And that does not create a problem, because the chemistry is actually really grafted on the surface. It's not sprayed on and therefore transfers to the other side. I think my understanding is that may be a concern.
And we also have solutions, well, it's engineering, not science anymore, but I can address that. We also have solutions where we have heads that are basically, one is in the upside down, let's say, and we can treat both surfaces in one shot also.
Yeah, also
that is also possible.
Yeah.
Thank you to you both. I hope, Marcel, it answered your question. In any case, you have Mark and Bernard contact details on screen, so don't hesitate to drop them an email. Next question is from Michael Schlum, who is asking, how does your process cope with volatile or mobile ingredients in the surface? For example, surfactant in a varnish.
So I'll take that one, Mark.
Yeah, please.
So we are indeed working with very tricky surfaces in some cases, some of which can indeed release over time some material, like exactly surfactant in varnish, or imagine something even more simple like PDMS that wouldn't be fully cross-linked and that still has some mobility. In that case, one thing we could do is like having a 2 treatment step. So, for example, the first step would be an actual plasma activation and cleaning, a bit like the Corona does, but at our range of energy, which would be sufficient to basically remove the volatile material, and after which we would apply our coating. And we have seen that with the coating, and that is very different from a surface functionalization with typical Corona. With the coating, we can actually avoid having the material that migrates at the top surface. If there is enough room for grafting with the actual substrate, it won't be a problem.
Thank you, Bernard. Next question is from Dominique Megassou. Is this technology relevant for 3D surfaces? I mean, complex geometries.
I think I've partially answered that question before. When it's highly complex geometries, then we may run into limitations. So we do need to be somewhat line of sight. We can let's say if you have a complex, let's say you have a bottle geometry, we can adapt nozzles to espouse to that, to adapt to that geometry. Those types of things we can fairly easily do, and we stay line of sight. Highly complex geometries going behind corners, that is not so easy.
Thank you, Mark. Next question. Did you also check the hydrophobic recovery versus shelf time on PP surface?
Yeah, that's a question that also relates to other questions. For example, some questions from Katalin Fotea, who was asking, a mere surface activation can be done only with the Corona discharge. Why the need for so much more? And later on, that person also asked, stated that Corona on PP lasts 6 months. Easily, in practical terms, the shelf life is 2 years. So I would like to take the opportunity to address all those questions at the same time, if you'll allow me to.
Yes.
So basically with polymers, and that's indeed what we fight against with coatings. The hydrophobic recovery is a phenomenon where the polar moieties that you graft with the typical Corona treatment gets buried in the material because it's actually unstable in air. Air is basically, to oversimplify it, air is apolar. If you have polar moieties at the surface, it's unstable. So what happens is that the polymer literally turns and buries the polar moieties. That's the hydrophobic recovery as I understand it. So with a plasma coating, that is an actual network that is literally grafted and built on the material. There's no such thing as hydrophobic recovery, and we have several proofs of that by simple characterization over time, and there's still months and months after which you still have the material, the same surface energy, the same efficiency regarding adhesion, for example, but not only adhesion. So, and to address the question of Katalin Fotea, I'm personally surprised to hear numbers such as 6 months and 2 years for PP activation with Corona. I'm not saying it's impossible, but I think that if you want that with Corona, you have to treat your surface like crazy so as to have a very high cross-linking degree of the surface to avoid the hydrophobic recovery. To me, that's the only way it's possible, and I think it is possible, but the customer we're working it, they cannot do that simply by virtue of the fact that the PP may be ultra thin, for example, and even with the Corona, at some point you're going to damage the polymer. Right? So the customers we're working with have this problem of storage, open time. They treat with Corona, they do it, and yet after days or maybe 1 week or two, they have lost it. So they're stuck with the material that they have to retreat. And that's the whole problem. And that's why some of the projects we're working on exist. And that's why we come up with that solution of organic chemistry that is grafted and that avoids the hydrophobic recovery. Not only to mention that we also have better efficiency, as was shown, and I think it was case study 2, Mark. We have better results than the Corona because we can. With Corona, you will graft mostly oxygen species, right? We can do other chemistries, and in some cases, with some glues, it's more efficient.
But I would like to add one comment. If the solution you have today with Corona works, then that's fine. Stay with that. Yeah, we are not. I want to make a very clear statement. We're not competing with Corona. It's when it doesn't work anymore. When it's not meeting your needs, that's when you come to us. We're not here to replace solutions that work well with Corona. We're the next step.
Thank you. We have another question from Katalin Fotea. What evidence for actual surface functionalization you have?
So, of course, we do characterize our coatings and our surfaces after simple functionalization. We have a lot of studies, some of which are done, some of which are ongoing. We use typical traditional characterization techniques such as XPS, for example, typically, but also we have a possibility to do tough sims. On the morphological aspects, we also check with microscopies, SEM typically, AFM in some cases. So there's a lot that has been done on that regard. And also, of course, we're sitting on a lot of indirect, but yet strong proof that it's working. For example, imagine what we do with the biomolecules deposited on gold, for example. I mean, it's really obvious that they're stable and well grafted. Of course, it's only indirect proof in those cases, but yet we are quite sure of the efficiency of our treatments.
Well, in those cases, we do the normal validation test just like you would do with any other deposition method, right?
Yeah.
Sure, it's there.
Another questions from Malolan Ramanjam. Are these coatings pinhole-free?
So that will strongly depend on the precursor you're depositing, but I must stress at the very beginning that the pinholes will not come from the plasma itself, like what happens in some DBDs. I've been working for years on that topic, and indeed, in some cases, you end up with pinhole-containing coatings, and the damage is done by streamers in the discharge. Here we have APGDs, so glow discharge or Townsend discharges that are streamer-free, and by the way, we're working in the afterglow, so there's no such things are streamers in the discharge. So the plasma will not result in the presence of pinholes. Now, it's true that in some cases with super reactive precursors and in incorrect conditions, we end up with non-uniform coatings. But the solution is just go back and do your homework, and you will find the conditions. I can show, I don't have one here, but we have tremendously, I don't know if it shows on the camera, unfortunately not.
It's a bit small.
Yeah, I'm sorry, but we have tremendously smooth and persistent coatings, uniform ones, when we work on the conditions and find them.
Yeah, if I can add a little add-on to that, so and to stress it, because to Bernard's point, there are some technologies out there where the material is run in between the electrodes of a DVD reactor, and then pinholes is a real issue, and then you have these streamers and etc. We don't have that because we work in the afterglow, and that was a technology choice. Actually, Vito did that initially as well. We chose not to do that for the pure and simple reason that whatever we want to build needs to be industrially robust from every perspective. That's the first. Second is, I'll give you a real example, concrete example, where we did a release coating, which is actually a polymer release coating that we put onto a substrate, which was then, first we characterized it to make, and we know it's pinhole free. Secondly, it was actually stretched bi-oriented, I believe 12 or 13x bi-orientation factor, and it was still pinhole free, just as a data point.
Thank you both. Another question from Katalin Fotea. Thanks for all your questions so far. How do you measure the layer thickness of the deposited layer?
So very simply, I don't know how experienced you are with plasma technology, and if you are, you will tell me that, of course, the deposition rate and the morphology and so on will be substrate dependent. But again, we're in the afterglow, so the effect of the substrate is very limited. I'm not saying it's in existence, but it's very limited compared to what we call a plasma zone, when your substrate is directly in the plasma between the electrodes, right? So basically what we do, yes?
If I may interrupt, because he's asking, the question is, how do we measure the layer thickness? Right?
I'm coming to that.
Oh, I'm sorry.
So basically, it's very simple. When we work with the new precursor, we deposit it on silicon wafers, for example, or on gold, and then you can do ellipsometry, and that we do with our partners. So basically, we know the deposition rates at the outset when we start working on a material. Basically, of course, I'm not going to do ellipsometry on paper or on non-wovens. That would be impossible, right? But on silicon wafer, you can measure very thin coatings in the nanometer range, right?
Thank you, Bernard. The next question is from me. Can you make coatings for gas barriers?
That's a nice one. It's actually, that comes up a lot. Typically, when you're looking at coatings for gas barriers, you're generally talking about inorganic coatings, be it SiO2-based, metal-based, those types of things. And those types of coatings require quite a lot higher energy systems than typically the range we work in. So on a whole, could we do it? To some extent, probably. Is it our focus area, and is it really in the sweet spot of the technology? I'd say no.
Thank you, Mark. Next question from Claude Mack. When treating fiber rovings, are you assuring that the fibers in the middle are also treated?
Bernard?
Well, so in the middle, well, there is a possible penetration in porosities up to microns in materials. If you're lower than that, of course, you cannot be sure that the activated molecules will, and the active species from plasma will actually efficiently penetrate the material. So I think that's to some extent, yes, but there will be indeed limitation to that. And of course, there will be obviously a gradient. What is in the outer region of the material you treat will be more treated than the inner range. And I think up to a micrometric porosity, it's possible. If you're below that, then I have doubts, to be honest.
Thank you, Bernard. And next question from Chris Griffin. To coat a continuous stripe of material about 10 centimeters wide, what line speed would be possible?
It depends. It depends, as I mentioned earlier, on which functionality, which layer thickness is necessary. But we're in that range of 10 to 100 meters a minute, depending on technical details.
Thank you. Next question from Thibaut Debussy. Are you already working on industrialized powder systems since today? Is it small batch? Do you have an estimation of planning before industrial scale?
Today we are indeed on batch systems, but the ultimate goal is indeed to scale up to much larger volumes. I think realistically you need to think that to have something reliable, industrially ready for large volumes, you need to be thinking 3 years, maybe 5 years from now, in that order of magnitude.
Thank you. Next question. Can you treat ID of glass capillaries with small ID, say 0.3 millimeter over a length of 30 millimeters?
Bernard?
Yes. So the answer is yes, we can. We are in a range where it's possible for the plasma and the chemistry to penetrate the material very efficiently, and we have been working on such let's say topics, or very closely related topics, and we've seen that we can indeed treat the inner walls of capillaries or whatever other material that are shaped like that. And the only thing is the problem is more of the engineering perspective, like, let's say. So scientifically it is possible. how to make it work is not necessarily straightforward. I'm not saying it's impossible, but there's a little work to be done up front. Right, Mark?
Yeah.
Okay, we have a few minutes left to take as many questions as possible. The next question is from David Tondero. Is there a risk of polymer intrinsic properties modification, like intrinsic viscosity or crystallinity?
Bernard, yours again.
I wouldn't expect that. I don't know exactly what we're talking about, if there's more specificity to that question, but no. And that's exactly how also we differ from Corona. We won't induce much damage to the surface of the polymer. We won't exceed temperatures such as 40, 50 degrees Celsius. So in most cases, we don't reach a TG or whatever of the polymer, so we don't induce changes in the mechanical or intrinsic other properties of the polymers. And by the way, in most cases, we don't even change the surface topography of the polymers, and we've seen that so many times.
Next question from Alan Coleny. Have you used this technology in food applications?
That's a broad question.
Yeah.
But yes, there are things we can do. That's all I can say. Not answer to a broad question.
Okay, another question from Malolan. Do you call air plasma as corona, or what is your definition for plasma and corona?
So corona discharges to us is indeed a type of plasma, typically formed in open air, but not necessarily. So air plasma, you can have a dielectric barrier discharge of air, but that will still be a plasma full of streamers with high energy and high temperature compared to what we call a glow discharge and low temperature plasma. Now, corona is a very specific type of plasma indeed. We know that it can be formed between, for example, a needle and a planar surface, and you will see those streamers forming at the surface of the planar of the metal. Sorry. So there's a difference between air plasma and corona. Not all corona are air plasma, and not all air plasma are corona. But indeed, what we tend to dissociate from is air plasma and corona. And why do we often use corona is because mostly what's done in industrial application is actually corona. Here we have different geometries and different materials. We have dielectrics, and we use nitrogen typically, or argon and helium for some applications, but mostly nitrogen. And we have something very different from a streaming containing plasma, right?
Let's take a very last question from Roland. When you use a defunctional molecule, do you know which function is on the surface of the material?
That's a fantastic question, and it's also very hard to address even when you have the means to do so, right? So in some cases, we can only put on an hypothesis saying, okay, from a purely thermodynamic point of view, this is most reactive. And that's what we're trying to do. We're trying to force the plasma conditions into having only one of the functions that react. Of course, we all know that's not exactly what happens. It's very statistical. So we're trying to locate the reactions somewhere without having it's not A plus B gives C plus D, right? It's not conventional chemistry. So very often it's based on assumptions, and then we try to control that, for example, by doing staining or derivatization with XPS and other techniques, but it's very hard to address, indeed. And that's something, that's a PhD thesis, and I think maybe several ones to address one case.
But if I would simply put, it's part of the art of what we do. Yeah, is doing exactly that. And in some of the chemistries we choose, we will have one functional side of the chemistry having lower energy bonds than the other side, so we can have some influence on that. Right, Bina?
Correct. Absolutely.
Thank you very much. Unfortunately, we are running out of time. Thank you everyone for joining us, and thanks for your great question. If we didn't get the chance to answer your question, or if you have any further questions, don't hesitate to get in touch. You have Mark and Bernard contact details on screen. I hope that you enjoyed the time with us and that you have learned something today. I also want to thank Mark and Bernard from MPG, as well as Marnik on the chat, who answer a lot of questions. Thank you to the three of you. The webinar was recorded, and the link will be sent to you immediately, together with a link to download the presentation. We look forward to welcome you during the fall for our next webinar. And in the meantime, I wish you a very good end of day and happy holidays for the ones who are on holidays soon. Thanks again, and see you again soon.
Thank you very much, Benjamin. Appreciate the opportunity, and for all the participants, please do not hesitate to get in touch with us. It'd be a great pleasure to find out what your pain points are, what we can help, which kind of value we can bring to your specific needs. We're there for you. Don't hesitate to contact us. Thank you very much. Thank you very much for participating.